original one, is also a fundamental matrix. So these guys are fundamental matrices of 1 prime, which is a special case of 1. So we know what? Very good. We know that by the lemma that there exists a constant matrix C such that these guys are related for any time by this matrix. Okay? Okay, that's okay. Now we're trying to prove what? We're trying to prove that the flow can be written in this form. So you need to give me a constant matrix R, and you have to give me this guy, and it has to be periodic and non-singular. Okay. So let's try to get a candidate for R. So I'll define R. It's a candidate. It has to be constant. So I'll define it to be 1 over T len this matrix C. Okay? And you know, we don't have enough time. It's just 2 lectures on this, the averaging and Floquet and whatever we can cover. So I'll not go through the existence and the, how to compute the logarithm of a matrix. So just read it on a side. So I'll define R to be this way. That's okay. Okay, you're giving me a candidate R. So please give me the candidate P and make sure that this happens. Okay, I'm gonna actually define P to make this the case. So I'm gonna define P from this equation to be phi multiplied from the right by e to the negative RT. Okay. So, and P is phi e to the negative RT with this R. So it's all based on this matrix that relates these 2 fundamental matrices. Okay. Okay, now it remains, so I have this is satisfied, everything is satisfied, but we need to show that P is periodic. And actually this is very important for the implications later on for stability. This theorem doesn't say anything about the stability. Okay? But we'll see why if we can write the flow in this form, then we can easily deduce stability characteristics. And this is very much relying on the fact that P is periodic. So we need to prove that it's periodic and also non-singular. Non-singular is super easy because this guy is invertible, obviously, and this is invertible because it's a fundamental matrix. So I need to prove that P is periodic. So let's prove that P is periodic. So P of T plus T, I need to show that it's equal to P of T. From its definition here, it's phi of T plus T e to the negative R T plus T. But you just said that phi T plus T can be written as phi of T times this guy C times e to the negative, here is e to the negative TR times e to the negative TR or RT, doesn't matter. And you can easily see that this guy is what? This guy's what? C inverse, right? Because there's negative 1. So this is C inverse, right? C from this definition, C is e to the RT, or large T. So this is just e to the negative RT, so it's C inverse. So that's great, because now I'm gonna go green here and cancel these C's, and this will be phi e to the negative RT, which is just P. So indeed P is periodic, and the theorem is proved. Let's see what are the implications. Any questions so far about the theorem? Okay. So the theorem is essential because of the following. It says that the flow can be written on this form. R is constant, P is periodic. This is the essence of it. So I can write my solution x of t. This is the implication. I'm done with the proof. X of t, which is phi of t times x of 0, right? Phi of t is just your P of t e to the RT. This is your phi, according to Floquet decomposition. Okay. And now, P, the fact that P is periodic, and actually it's continuous as well. Why continuous? Because look at its definition. This is P. Phi is the solution of the differential equation. It's more than continuous. And this matrix is very super nice. It's actually same thing. So this guy is at least continuous, more than continuous actually. Periodic and continuous implies that it's bounded. It can not blow up. And if this term is bounded, I know for sure that it will not blow up. This guy I know very well, e to the RT with R is a constant matrix. This is, our paradise. What do you know about that? What do you know about if the eigenvalues of R, what do you like for them to be? So the real part of them, they should be strictly negative. This if and only if implies what? That this matrix is decaying, right? And if this guy is decaying and the other term is bounded, then x of t goes to where? P to the RT decays, and this is just multiplying by some term that is bounded, and this guy will decay for whatever initial condition you have, right? So x of t goes to 0 as t goes to infinity for any initial condition. So we got what? So we got global exponential stability, right? So here is, you can say it's a corollary or whatever, but the main result is that the system 1p, the periodic system, linear time periodic, is globally exponentially stable. Of course, we're talking about the origin as well as any solution. Exponentially stable if and only if this happens. The real part of the eigenvalues of the R matrix are all strictly negative. So we got this is an sufficient condition for stability. Okay. It just remains to see how to compute this R. And so I have a system, which means I just have the A matrix. So please tell me how to compute R. Okay. And I'll check its eigenvalues fine. So let's see how to compute R. Any questions so far? We actually have R from the definition. So what's R? R is 1 over T ln C, right? And what was C? Well, C was the relation between phi t plus T and phi just T. So in particular, I can talk about just phi of large T. So I substitute phi of 0. Without loss of generality, I can take this guy to be identity, the normalized phi. So this means that my C is just the solution after one period. Go simulate your system, give me the solution after one period. This is phi of t that we're going to use, and it has a special name. It's called the monodromy matrix. Its eigenvalues, the eigenvalues of the monodromy matrix C, are called the Floquet multipliers. So if you have C, please take the logarithm of it, divide by just a number, get your check the eigenvalues. Okay? And because we know the relation, this relation very well, I can actually work on the C directly instead of taking the logarithm, because here C is e to the RT, right? I want to check the eigenvalues of R if they are in the left half plane or not. This corresponds to the eigenvalues of C lie where? So say scalar case. R is -1. So the eigenvalue of R is here, -1. This is a stable system, everything is fine. E to the -1, if even t is 1, so this is lambda, here is lambda c. E to the -1 is 0.37, it's here. This mapping e to the something, it maps the open left half plane to where?
The unit disk.
Exactly. Maps this guy to the open unit disk. Okay? So just check the eigenvalues of C directly. Please go and simulate your system for one period. Get this matrix. Check the eigenvalues. They must lie in the unit disk, and that's it. Okay? So again, this result I can repeat it and say if and only if the eigenvalues of the monodromy matrix, which is the solution after one period, the absolute value is strictly less than 1. Okay? Any questions so far? We're done with this result. I'll just give different perspectives of it. Okay, it's this exact same result. We will not do anything different than just getting the eigenvalues of the monodromy, which is the Floquet multipliers, check that they are within the unit disk. But I will give different perspective.
So, Professor, if they are on the unit disk, or if I have any zero on it,
it's critically stable. It's not exponentially stable. This is a pure linear system, so you're comfortable to say critically stable. But if it's a linearization of a nonlinear system, then the analysis is not conclusive. So a different perspective. What is x of t? Well, x of t for any linear system is 5t x of 0. Without loss of generality, I assume that 5 zeros are identity. Okay? And what is 5t? What is 5 large t?
P of t, e to the power of.
This is just c, right? We just call it c. It's a constant matrix c, x of 0. Can you give me what is x of? This is I'm saying this is the monodromy matrix. 5t is the monodromy matrix. Okay. What is x of 2t? Well, again, it's 5 2t. It doesn't matter. X of 0. This is the very nice thing about the linear systems. And because it's periodic, or even without being periodic, 5 2t can be related to 5t with a constant matrix. In this case, for the periodic case, it's indeed c, right? X of 0. And what's this guy again? C. So this is actually c squared times x of 0. So x of nt is actually c to the n x of 0. And you can write this as x of k plus 1t is equal to c x of kt. So this is xk plus 1 equals a matrix constant, just numbers, times xk. This is an LTI, but it is discrete time, right? It's a discrete time system. Anybody saw before discrete time systems? You do the Z transform instead of Laplace, and so what's the stability criterion for this system? Xk plus 1 equals a matrix times xk. What's the stability criterion? Eigenvalues of this guy like the unit disk, which is what we got from the Floquet. So this system actually represents the discrete time version of the continuous system, with t being the sampling period, if you're familiar with this notion. Okay? Any questions so far? This is a little bit different perspective. And another different perspective that is very, very useful in the extension to the nonlinear case, and it's very nice here. What we're gonna say now is, let's consider x of t. I'm doing a transformation now. I have a system that is time varying, and I'm doing a transformation, and I'm giving you a magic transformation that is actually given by just this p that we're talking about. So I'm transforming from x to y like we do in linear systems all the time. But this time is a time varying transformation, which is not very weird because the system is already time varying. Okay, so let's get the y dynamics, please. The y dynamics, so let's differentiate. So x dot is p dot y plus py dot, and this is equal to, because x dot is ax, so this is a times x, which is again py, right? This is how we always do it. And then let's get y dot in one place. So this is P inverse APY minus P dot Y, okay? Let's expand things. Remember, P is phi e to the negative RT. So let's expand things, please. So I have here Y dot equals P inverse of A times P. P is phi e to the negative RT. Times y, I'll take the y's, all these y's I'll take it as a common factor. Minus p dot, let's say p dot. So here is p, and both are time varying, so it's actually two terms. Here's the first term, phi dot. The second term I have phi, and I have negative r, so this is positive r, e to the negative rt, and all multiplying y outside, okay? Phi is a fundamental matrix, so this is a phi, right? And you can see now right? A phi e to the negative RT, this is A phi e to the negative RT with A phi e to the negative RT. So they go all together, right? And we just left with P inverse. And let's expand P inverse as well. What's P inverse from here? So P inverse is e to the RT phi inverse multiplied by phi r e to the negative RT. Why? And you can see here, obviously, phi inverse goes away, and we have e to the RT or e to the negative RT. Anybody remembers from the characteristics of exponential? Anybody can remember what's that? It's actually just R. So the Y dynamics is RY. This is an LTR. We transform the time varying system to a time invariant system. And they go hand in hand. Why? Because if Y goes to 0, from the very first definition consider, if Y goes to 0, X will go to 0 because P is bounded, right? And vice versa actually, because P is invertible. So if X goes to 0, Y goes to 0. So this system is stable if and only if the original system is stable. And I know very well how to check the stability of this guy. This is LTR, and the eigenvalues of R should lie in the left half plane, which I know from the Floquet decomposition. But the point here is that I managed to transform a time varying system to a time invariant system. Exactly, there is no approximation. It's an exact transformation. So I can work here very fine and just ignore the time varying system and look at the following property. We have one more property. What is y of t? Can you give me y of t? What's the solution of this guy after time t? What's it?
E to the power of t.
E to the power, right? Rt times y of 0, right? And what is the solution of my x of t? Was what? Well, we just said from before, x of t was c x of 0. Yes, but actually this is c. So what do you mean here? We mean that the flow after one period exactly the same. If you start with a point x naught and flow along the original differential equation, so this is the flow map that we talked about before, along this a of t was our dynamics a of t times x. For time t, I will reach a point t. And if I flow along the time invariant system, which is much easier to compute, so this is flow along r times x or r times y, okay? For time t, I will reach the exact same point, okay? So the flow along the time varying system for one period exactly equal to the flow